Well, thank you very much. I really appreciate being invited to this seminar series. It's actually been a phenomenal opportunity for me to learn more about what's going on in the UK, and we found a lot of great overlapping interests already, so it's been very exciting. So today I'm going to be talking a little bit about how topology relates to more complex chemical systems and trying to kind of think about creative new ways to apply topology to learn more about things like hierarchical organization and understanding complex reaction coordinates that can occur within complex chemical systems. And so first, I just want to kind of let's address the question of what are complex solutions. And so according to my definition, basically, these are any kind of multi-component solutions that range all the way from, and let me actually put on my laser here. Hopefully this will show up as a little laser for you guys. This goes all the way from chemical solutions that have local correlations, just like kind of saltwater type solutions, to when you have amphiphilic molecules that may self-assemble, to phase separation type of systems, so biphasic systems, or systems that are highly structured, for example, colloidal types of fluids. And so in thinking about the nature of complex solutions, we have this really unique property associated with kind of hierarchical behavior in the correlation of molecular properties and motion and behavior. So all the way from the local to kind of the global rheological kind of scenario. And so if you're interested more in kind of classical simulation methodology, because all of this is done with computational chemistry, you can see a recent PCCP perspective article that we have that talks a lot about kind of ways in which you can do simulations on these types of systems. So a really interesting and important point is that complex solutions often have very large, what we call ensembles of different kind of molecular scale or even hierarchically organized species. And so this is just kind of a normal distribution representing some kind of ensemble of all of the different kinds of environments and chemical species that you might see in a complex solution. And these vary across length, scale, and shape and morphology. And we have, local environments, we have intact molecular species. If we have molecules that are capable of aggregating with one another, we might have supramolecular assemblies, or under concentrated solutions, we might have networks of interactions that can be present. And sometimes you can even have very large kind of species that might be like nanoparticle type things. So the point is that there are many, many, many different molecular environments, and depending upon the complexity of the solution and the ensemble of all of the environments that are present can be quite large. So another important thing to recognize broadly, and I think chemists have a really good notion of this, but it's something we often take for granted, is that the ensemble of all of the molecular species that we observe in a solution is directly related to the underlying potential energy landscape that we've already heard a little bit about in the previous two talks. And so, the populations that you see of specific molecules that might be observed either via experiment or theory, correspond typically to minima on that energy landscape. Obviously, chemical reactions are going over barriers towards other minima on that energy landscape. And there can be many contributing factors associated with the topology of the energy landscape. What constitutes a barrier? Why do you have an interconversion between species and things like this? And so there's a very fundamental notion here that if we want to understand and predict reactivity of chemical systems, having a very good understanding of both the ensemble and the energy landscape is incredibly important. And for us, within our research group and in a lot of the projects that I participate in, we want to be able to understand and predict reactivity. And we also want to understand how we can tune or modify the energy landscape topology based upon different chemical conditions, solution composition, things like this. And so in thinking about kind of a theoretical framework for tackling this connection between the ensemble and the energy landscape, there's really kind of two approaches that you can take. The first is to try and characterize the energy landscape to understand the ensemble distribution, or the opposite, to characterize the ensemble distribution to understand the energy landscape. And we're going to be talking today about a couple of approaches within a couple of tasks, objectives within each of these approaches. So first, I want to highlight the complexity of the energy landscape, because often as chemists, we've already mentally used our chemical intuition to reduce its dimensionality. But in reality, the potential energy landscape is a 3n dimensional function, right? That's mapping all of the Cartesian coordinates associated with all the particles in the system to changes in the potential energy. And so, we often, for small molecules, we might remove translation or rotation to create low dimensional examples, as I've gotten here for water and oxygen. But then oftentimes chemists, we say we're interested in a specific chemical reaction, and we automatically kind of project out all the other dimensions of interest to focus only on the barriers and minima associated with a specific chemical reaction. But the raw dimensions of this energy landscape can be very, very large, obviously, if it's 3n dimensional. And by the time you get to things like catalysts or proteins or transformations at interfaces, you can have just a ridiculously large amount of raw dimensions associated with this energy landscape. And so if we want to characterize the behavior of an energy landscape, one of the first tasks is to reduce its dimension. And we recognize that many dimensions are not relevant. And for simple reactions where you've got distances that might be like a bond breaking formation reaction kind of coordinate, geometric parameters can be excellent reaction coordinate variables. But oftentimes in these complex solutions, we have collective motion of the solvent that participates explicitly in the reaction itself. And so there is, I think, a very strong need within the community to try and develop what we would call higher dimensional reaction coordinates that can capture this collective motion across many, many molecules, depending upon the amount of organization that's present in this solution. And so the approach that we've taken has actually been associated with not molecular graphs in the context of graphs of intact molecules, but we would call what we call intermolecular graphs. And so we focus less on the atomic positions and more on the intermolecular interactions that are present in these complex solutions and studying the patterns and dynamics of these interactions. And we want to use these patterns as a way to develop new higher dimensional reaction coordinates. And so the way that this typically works is we take our Cartesian coordinates from our molecular simulation data. We employ some criterion to define the interaction, hydrogen bonding, dipole ion, ion, whatever have you type of intermolecular interaction that's present. And from that, we create a graph of the intermolecular interactions where the molecules are nodes, molecules, or sometimes assemblies. We can coarse grain this graph as well. But those molecular species become nodes and the interactions are edges. And if we have a time-dependent series of coordinates, like you would have, say, from something like molecular dynamics simulation, then you have a time-dependent network. So now you have this network formalism, and you say, okay, well, I would like to develop descriptors that recognize the patterns in these interactions so that I can then capture this collective motion that's occurring during a reaction, say, in a complex fluid. And to achieve this aim, we've turned to spectral graph theory. Now, spectral graph theory just means that we're talking about the eigenvalues of the adjacency matrix or the degree matrix of a graph. And so here's a really simple graph. The degree matrix is just the n by n matrix that shows the number of edges that every single node has in that graph. The adjacency matrix is actually like the pairwise list of all of the edges that are between every pair of nodes that are present. And so in spectral graph theory, the idea is, well, if we're looking at the eigenvalues of whatever the matrix representation is of the graph, then that the eigenvalue spectrum and the eigenvectors are going to be representative of the patterns that are present in the graph as a whole. Oftentimes the Laplacian matrix is what's studied, and the eigenvalues of the Laplacian, which is the degree minus the adjacency matrix. And from this, there's a huge range and a very broad field associated with people that study the spectral properties of these types of graph matrix representations of the graphs. And so for us, we decided to look at eigenvalues associated with the adjacency matrix or modification of the adjacency matrix. And we turned to the Google Internet search engine as a way to help us in that process. And in the original implementations of the kind of Google Internet search engine, they implemented something that they called PageRank. And so PageRank, basically the whole intent of this process from a historical perspective was, you've got this graph based upon websites that are all connected to one another via hyperlinks. And they wanted to have kind of two things. The first was that they wanted to have a descriptor that was a unique identifier of connectivity of the nodes that are present, the websites that are present, and all of the hyperlinks they might have. And they wanted to be able to have some kind of weight function that came out of this, which ends up being an eigenvalue that represents the extent of connectivity. And so I'm going to go through a little bit of the derivation of PageRank in a few minutes, but the main concept here is that if you have a graph and it has a unique adjacency matrix, which means that it's not isomorphic, then it will have a unique PageRank value. And so this process really starts very simply, and I'm going to go through this really quickly. You have your graph and you have your adjacency matrix, and you divide it by the number of links or edges that each node has to create a column stochastic matrix. And then this column stochastic matrix has this beautiful property according to the Perrin-Frobenius theorem, where the 1 is the largest eigenvalue, and the eigenvector that has the eigenvalue of 1 only has positive entries, and all of the sum of those entries is 1. So in some ways, the cool thing about this is it's like an internal normalization in some way. You are bounded, the entries to the eigenvector that has an eigenvalue of 1 are bounded between 0 and 1. And so the eigenvector entries that have a much larger, higher number associated with them mean that there's more connectivity associated with that node than one that has a much lower, lower number. So this internal normalization is very, very useful to us. And then Google, for its purposes and the nature of the graphs that it was studying, basically introduced and created this Google matrix, which was a slight modification of the column stochastic adjacency matrix, where they added this kind of dampening factor D into their matrix. And this was because in the internet, in the graph associated with the internet, very similar to the graphs that we have in chemistry of intermolecular interactions, there can be a lot of dangling nodes, meaning nodes that don't have connections or may not, like in our case, molecules that may not have specific interactions that were of interest. And so this factor helped them in a couple different ways. It helped them actually in their solutions for actually solving the eigenvalue problem itself. And it also kind of had a social kind of science implication in the sense that they felt that the dampening factor was kind of like a likelihood that a person was going to actually click on a link to a node, to a website within their graphs. And so for us in the context of chemistry, the PageRank implementation was very useful because of this linkage between a unique adjacency matrix, the internal normalization that occurs within the eigenvalue calculation, and what we know about chemical properties and geometric arrangements around atoms. And so all of us as chemists know that, the coordination around atoms and ions is very well organized, and we have these beautiful theories like valence shell electron pair repulsion theory that tells us that molecules and atoms arrange in each other as regular polygons. And it turns out that regular polygons have unique adjacency matrices up to a pretty large number of vertices, up to about 13. And so when we applied this and adapted this to chemical applications, we initially used it as kind of a data mining tool where we could pull out, we created a library of all possible PageRank values for all possible polygons, and we could run a complex molecular dynamic simulation of like a concentrated electrolyte or something like this, and we could pull out all of the geometries around all of the ions that were present in that solution. You can, and we've applied it to many different types of chemical phenomena, understanding ion pairing and changes to geometry and reactions and things like this. But that's not the only utility associated with this kind of spectral graph theory approach, in the sense that if we modify this approach a little bit further, we can then start to achieve our goal of trying to understand and create reaction coordinates that are sensitive to the changes, the collective motion and collective changes in intermolecular interactions along a reaction. And so the way in which we do this, originally in the PageRank formulation, we were using unweighted graphs. However, if you turn to a weighted graph formalism, then it allows you to have, obviously, and the weights are based upon the strength of the interaction between molecules. Then you have now entries in your adjacency matrix that are non-integer. And when you reformulate PageRank and that eigenvalue calculation for a weighted graph, you actually get a smooth, you get one of the characteristics you need for a reaction coordinate, which is a smoothly changing variable as a function of the changes to the interactions that are present between molecules. And so what we have now is a map between the eigenvalues of the adjacency matrix and the Cartesian coordinates. And we are able to directly calculate the forces in PageRank space associated with molecules as they're progressing along a chemical reaction. This allows us to map out the free energy landscapes of complex reactions that are occurring in solutions. This has also been done in a slightly different way with Sprint, with what are called the Sprint collective coordinates, which were published, oh goodness, I was in around 2012, 2013, and I should have had the reference on there. I forgot about that. So just to give you an example of how these spectral graph theory kind of topological based reaction coordinates can help you understand more about the chemistry, if we just look at a really, really simple chemical reaction, just ion pairing, sodium hydroxide, say ion pairing in water, and you can probe this reaction energy landscape just using distance, and you can probe this using PageRank. And so PageRank is capturing all of the changes in the hydrogen bonding network and the solvation associated with these ions as you bring them together. And then you can look at what forces are contributing the most to the free energy landscape. And in fact, we can very clearly see from the JCP paper that got published last year that solvent reorganization and the forces associated with solvent reorganization are dominating the free energy landscape, and only very, very specific portions, actually right here, are dominated by the distance coordinate. And so within our group, we're building a library of these graph topological reaction coordinates that are trying to encompass the collective motion of complex solutions. So that takes care of kind of that first piece, which is how do we reduce or is addressing some of that first piece, which is how do we reduce this very high dimensionality associated with the energy landscape. The next question is how do we encode the topology of these reduced energy landscapes to learn something new? And we've already seen some really beautiful work associated with energy landscapes, and I'm going to kind of build upon that. And so I'm very thankful that Ingrid talked before me. But let's just talk for a little bit about how our complicated energy landscapes typically represented in a mathematical or graph theoretical way. And so often, especially within kind of the protein folding literature, the representation of complex energy landscapes is given with merge trees or disconnectivity graphs. And so I have here on the left-hand side an energy landscape where each of these black dots is an energy minimum. And then we have different critical points that are connecting these minima. And some of these critical points are of index 1 and some of them are of index 2. Now, in a disconnectivity graph, you follow basically the red lines right here, which are just basically the lowest energy paths that connect one local minima to another local minima. And if you have multiple connectivity paths between different minima, that disconnectivity graph only chooses the lowest one. In contrast, you've seen a little bit about persistent homology, and I'm going to build upon this further in a second here, but it is possible to create a barcode representation of the energy landscape, and I'm going to show you how in a second. And in that barcode representation, you saw earlier in the earlier talks about zero-dimensional features and one-dimensional features, but with the barcode representation, we can actually capture much more information of all of the pathways that connect different local minima, going through both the index 1 critical points as well as index 2, and this is captured in the one-dimensional persistent homology. So how do we, but before I talk about how we get to the persistent homology, there's another thing that's important about merge trees, and this is that two different energy landscapes can have the same merge trees. And this is because the merge tree is only following that lowest energy path between minima. So how do we create a persistent homology barcode of an energy landscape? Well, we're using a technique called sublevel set persistent homology. And if you imagine that you have kind of an energy landscape and we're kind of starting at the minimum of that energy landscape and we're kind of filling it up with water, we're going to see that the components, which are the minima on that energy landscape, start to grow and merge as we fill this up with water. So let's say we have lots of minima and we're starting at the bottom, we're filling up our bathtub with water. And this is this right here is the lowest energy minima on the energy landscape. We fill it up with a little water, a little energy, and we start to see other local minima that are present. These are new components that present themselves in our persistent barcode. We fill it up even more. We see more of the bathtub features kind of filling in. And then eventually, as we fill our bathtub of our energy landscape with energy, they start to merge with one another. And they form holes, and these holes are the blue bars, the one-dimensional features. And then eventually we filled up our entire energy landscape. And so this is just another representation of that for this energy landscape. And we can connect, actually, for simple molecules, we can connect these minima to well-defined, for example, conformations within the conformational spaces that Ingrid was talking about earlier. And so, you know, you can do this we've done this for actually the N-alkanes, and you'll see why we focused on the N-alkanes in just a second here, but you can go to systematically more and more complex molecular structures and more complex energy landscapes, and you can map out the sublevel persistent homology barcodes for those. Now, something that's really interesting about this chemical system, although it's very, very simple, is and an idea, a notion that we had is, you know, many aspects of the energy landscape are really about the conformational degrees of freedom of molecules. That's is like within a single molecule itself, right? And so there is a concept that you could say, well, you know, let's say I have something like butane, and I systematically add carbons to it to create increasingly longer chain alkane molecules. You know, the underlying degrees of freedom of butane are present in pentane. And the underlying degrees of freedom of pentane are present in hexane. And what this causes is a specific pattern in the sublevel set persistent homology barcode. And you can use this pattern to your advantage to actually prove what the energy landscape, the conformational energy landscape of all N-alkanes actually looks like. And this is because of this concept of embedding. And so this is what our collaborator, Henry Adams, and his team did from Colorado State University. Really, really lovely work. And now we're extending it to think about, okay, well, now what if we want to mix and match different conformational degrees of freedom that might be present in different molecules? Can we use the patterns in simple energy landscapes based upon conformation to predict conformational energy landscapes of much more complex molecules? There's also a concept associated with distance, which was brought up in the first talk today, which I was really grateful for, in that, you know, from a mathematical perspective, a distance is, you know, you're inputting in, you've got some function that takes two inputs and you're trying to understand the difference between those two inputs. In this case, our inputs are sublevel set persistent barcodes. And what we have here are two sublevel set persistent barcodes for the conformational landscape of hexane. One is based upon the analytical potential for the internal conformational motion of hexane. The other is from molecular dynamic simulation. And so we know from simulation data that we often can't sample all of the energy landscape perfectly, right? We have this concept of that there's always going to be some missing pieces. And so we've introduced and compared some different elements, different descriptions of distance to try and kind of quantify, you know, what are the differences in the energy landscape if I sample energy landscape function versus having it analytically. And we examined edit distances, so the bottleneck distance and the Wasserstein distance that was brought up earlier. And you do find different kind of fidelity levels associated with different distance metrics. In particular, the Wasserstein distance, which is kind of a metric that measures it's also called the Earth mover's distance. It's basically measuring the amount of work to transform one distribution, in our case, one barcode distribution, into another barcode distribution. And this was much more sensitive. The Wasserstein distance was much more sensitive to the fact that our molecular dynamic sampling of the barriers of the conformational landscape of hexane was much poorer than something like the bottleneck distance. And so we're exploring these notions of distance to try and come up and evaluate what are really good notions of distance to be able to quantify variations in energy landscape features. And so what we want to do is we want to be able to quantify these variations in energy landscape topology between related systems in complex solutions. And we learn based upon what we learned for the alkane case, and as we're slowly building up kind of our molecular understanding and learning the fundamentals, we're really excited about the applications that this could have in more complex solution-based frameworks. The other thing that I think is really interesting is, and this was brought up, vectorization was brought up previously, is that these descriptors, the barcode representations and kind of vectorized representations, are very amenable to things like machine learning frameworks. And what we would like to get to in our future is kind of using these descriptors and representations of energy landscapes to be able to predict variations in reactivity, kind of tune, for example, solution composition. And this is done in collaboration with my mathematics colleague, Bala Krishnamurthy at WSU, and we have a shared mathematics student, Enrique Alvarado. So I want to end with talking a little bit about moving forward with different concepts of topology and chemistry. And so you've seen here a bit about graph theoretical topological descriptors of intermolecular interactions and how we're kind of really interested in using these to understand collective motions. You've seen some sublevel set persistent homology to encode energy landscape features and how we might quantify variations in energy landscape. But what about analysis of geometry? And so there's many tools, right? Geometers have been around a really long time associated with studying the properties of geometry. But in complex solutions, there are actually some really interesting features and things that can emerge that challenge the current notions of how we might try and quantify geometric features in a system. And so in particular, I'm going to focus on the hierarchical organization that can occur at a liquid-liquid interface. And so when I say liquid-liquid interface, I mean something as simple as just oil and water. But at a molecular scale, you know, we're seeing the macroscopic on the left-hand side, but at a molecular scale, there's a huge amount of complexity associated with the instantaneous interaction surface between these two solvents. The study of liquid-liquid interfaces has tremendous impact across many areas, whether it's drug delivery and understanding how things can go across cell membranes, or you know, the properties of cells at all, you know, in the context of budding or vesicle formation, to solvent extraction, which is arguably the kind of the world's largest purification, the most industrially used purification process. You know, solvent extraction and distillation are kind of like the workhorses, right, of chemical synthesis, purification, and things like this. And so in solvent extraction, you have two different immiscible solvents, and you have a complex mixture of solutes in the aqueous phase. And then in the organic phase, you have some kind of molecule that will preferentially bind to the solutes that come up to the interface. And when they bind, they change, the nature of the hydrophobicity changes. The free energy of solvation changes of those molecules to go from being preferred in the aqueous phase to preferred in the organic phase. And so they migrate into the organic phase. At a molecular level, at that instantaneous oil-water interface, you have all of these really crazy hierarchically organized structures like this protrusion right here, as well as what we would actually call kind of like hinge-like molecular machines, which hopefully I'll be able to get to in a few minutes here. And so this liquid-liquid interface is very rough. It has surface roughness, and there's two types of roughness that are present. There's long-range capillary wave features, and there's short-range thermal roughness. And you can have this assembly, kind of self-assembled structures where you have lots of intermolecular interactions that cause kind of spontaneous hierarchically organized features. And so you can see this if you have just a simple water hexane interface with no surfactant. You can just kind of see some of this roughness. You add a surfactant like tributyl phosphate, and you get these cusps and peaks that emerge, and they actually end up turning into protrusions that allow for solute transport. So we had this range of low-lying kind of fluctuations that occur at the aqueous organic interface to increasing collective organization and dynamics until you have well-defined surface macrostructures. Now, given the fact that you've got a rough surface and you've got structures on top of a rough surface, it is actually incredibly challenging to identify these macrostructures. Typically, this is done only by visual inspection, and sometimes people try to impose surface curvature rules, but this is very also kind of kludgy and not not really amenable to if you want to analyze very large data sets. And so, we want to be able to robustly identify these species, then characterize their morphology using things like persistent homology. And then if we are able to do this, then we can ask a whole slew of really fascinating chemistry questions. Are there specific assemblies that facilitate transport? Are there certain shapes of structures that cause transport? Can we tune the transport mechanism by changing the composition and molecules that are at the interface? And so the tool that we've applied to this purpose is called geometric measure theory. It is a tool within the field of geometric measure theory or geometric measures, and it's called the flat norm approach. And this flat norm approach has been employed in like image denoising types of technologies and things like this. The idea here is, let us say we have a curve or a function that's in R2. I'll give you the R2 case first, and then we'll do the R3 case. But we want to be able to systematically peel off areas off of this function. And we want to have, it's an optimization where we want to find the smoothest function underneath once I peel off a specific area. And so the amount of area that I peel off is given by this variable lambda. And I create this smooth function underneath. So what's the optimal smooth function underneath this one? So a little bit more complex of an example that's a little bit more amenable to my interfacial systems. Imagine I'm looking kind of in the 2D slice at my liquid-liquid interface, and I have this complex organized structure here. I can optimize or find the minimum curve underneath, taking off a specific area. And I've got two examples here where I've got an initial lambda 1. And in the initial lambda 1, I've taken off this the brown areas here and to create the green curve underneath. And then I can change lambda 1 to be I can change lambda to create and do this again with a lambda 2, which curves off another huge amount of area. Lambda 2 is much, much less than lambda 1, and it's peeling off a much larger area underneath this curve. So our surfaces are obviously in R3. And so within our kind of computational workflow, what do? We take our molecular simulation data. And the first thing that we have to do is we have to discretize the surface into kind of a tetravolume mesh. So this is an image of the water part of an oil-water interface. And we had to go through quite a lot of algorithm development because, initially we thought, oh, wow, well, one lambda will work to be able to kind of carve out these volumes. And in fact, that is not true. And part of the reason why it isn't true is because these surface structures have such a huge range of shapes associated with them that no one symbol lambda peeling off a specific volume will do. Another way to kind of conceptually think about this lambda is it's like you're rolling a ball underneath the surface, and the surface has a radius of 1 over lambda. And so as I roll the ball underneath the surface, I'm peeling that area that I rolled off is the volume that I'm taking off from my interface. And so we had to take a probabilistic approach kind of based upon this analogy to a rolling ball in a mesh, where we systematically decrease our lambda value, and we keep track of at every single lambda value, we have our list of components, which are the features that we've peeled off of our interface. And we keep track of these components and how they merge with one another as a function of this lambda value. So we're tracking our components as a function of lambda. We also monitor the volume of those components because if I've got a bunch of components, as I peel off the volumes, eventually those components merge and they become connected. And so we had to impose some threshold volumes associated with the connected components that were based upon this. And so here's another, so we kind of have in this probabilistic workflow, we decrease our lambda value, and this ratio here is basically the volume. It's a ratio associated with the volume we've taken off of our surface versus the volume of our ball. And so we're kind of scanning through kind of how much volume are we taking off as a function of lambda. And then we have a lookup table of all the components that we peel off as we do this. And the premise here of this probabilistic kind of approach is that if a component stays present through a wide range of lambda values and volumes that we're sweeping over, there's a pretty high probability that it is a bona fide molecular structure on the surface or hierarchically organized structure on the surface that we're interested in for the purposes of learning new chemistry. And so we have probabilities associated with this, and we rank these probabilities basically. And by eye, we had a set of about 200 protrusions, these surface structures that we had identified from our simulations. And we basically looked to see, okay, how well is our code working in the context of, can it find all these protrusions? It was able to find all of them. You start to get false positives after about kind of the middle of the ranking between all of the structures that you get. But obviously, the higher the ranked species, the more likely it was for us to say, yeah, visually by eye, I think this is in fact a surface structure. And so we're doing some modifications to this, but we can analyze, hundreds of thousands of frames of data in this way, hundreds of thousands of protrusions in a pretty computationally efficient manner. Now, I'm just going to end to tell you a little bit about the impact of this and what you can do now that we can identify these protrusions. What can we do? And so I want to talk with you about the water octanol interface, and this is actually octanol in octane. And so I've got a series of simulations where you can see different types of structures that form on the surface based upon the concentration of octanol and octane. So with 20% octanol and octane, you just kind of have a normal rough surface that occurs between a water organic interface. At 40% octanol, you start to see these protrusion-like things form. And at 80% octanol, you get what we call a partial bilayer that's formed. And between this 40% and 80% number, the change in the geometry and the organization of these hierarchically organized species changes the transport mechanism. And you'll see that in a second here. And so this is just to kind of show you, I'm going to show you the highest, the 80% octanol case right now. So you can see the transport mechanism. I don't think I have enough time to show you the other one. So let me just tell you right now, this 40% octanol case, you get with this protrusion structure, like these guys, okay? And these guys break off and transport water into the organic phase. So that's what happens at 40%. So let me tell you what happens at 80%. At 80%, we can look at the water octanol structure, and you can kind of see that there's like this partial bilayer type formation. And the first layer, the layer of octanols that are directly in contact in water, are pretty homogeneously distributed. However, the second layer, the layer that's in this partial bilayer structure, you have these things called bilayer islands that form, where you have well-organized kind of octanols that are stuck together. Then you have these gaps before you form another island. And it turns out if you follow the behavior, we can identify these islands really easily, and we can identify all of these surface structures. And if you follow the behavior of these bilayer-like ions, they behave really interestingly. So we've got, this is an octanol that is kind of in the first layer. It binds a water, then it swings up, and it swings up into a bilayer island. And then that bilayer island, a portion of it swings back down into the first layer that's in direct contact with water. And so this is what we would call a molecular hinge for water transport. So we have the right balance of hydrogen bonding interactions between octanols that facilitates those octanols coming together, binding a water, swinging up, releasing the water, then swinging back down again. And this is a very reproducible phenomena, and it's well modeled using just a double harmonic well and Langevin dynamics. And so this is kind of akin to a molecular machine. It's not doing work in the sense that you're creating, like it's not moving uphill. This is an equilibrium-based process, but it is a molecular hinge basically for the transport process. And it has the same kind of underlying energy landscape as molecular shuttles do. So hopefully, kind of in summary, hopefully you've seen that we can kind of really think about the shape of data in chemistry in lots of different ways, and that those ways can help us become better chemists. Hopefully that you've been able to, I think from the previous two talks, and hopefully from my talk too, that, if we think about topology broadly, we can incorporate graph topology, we can talk about the topology of known functions and sampled functions. We can think about geometry from a mathematical representation of molecules perspective, as in the conformational spaces work that Ingrid talked about, as well as things like geometric measures. And there's just a tremendous opportunity for expanding these techniques to elucidate new chemical phenomena. And so with that, I just want to thank kind of the teams of people that I work with. And so I've got a kind of core team of people that works on complex fluids and interfacial kind of separation-based processes with some wonderful collaborators. And then that's funded by the Department of Energy in the US, and we have some supercomputing facilities that we utilize. And then the descriptors of energy landscapes based upon the sublevel set persistent homology has been funded by the National Science Foundation, and it's through a project called Descriptors of Energy Landscapes using Topological Analysis. And the work that I showed was a particular collaboration with Henry Adams at Colorado State, Marcus Flom at University of Colorado Boulder, and YZ at Urbana-Champaign. And so with that, I'm happy to answer any questions, and I really thank you for your time. Thank you.